Since the dawn of time, humanity has looked up at the stars and wondered, how did it all begin? How did this vast expanse of space, filled with galaxies, stars, and planets come into existence? This question has puzzled philosophers, theologians, and scientists for millennia. It's a question that takes us on a journey back in time, to the very birth of the universe itself. Today, we're going on that journey. We're going to explore the theories and evidence that scientists have gathered in their quest to understand the origins of the universe. So sit back, look to the stars, and let's delve into the fascinating story of the beginning of everything. So how did the universe begin? The Big Bang Theory. The Big Bang Theory is the prevailing cosmological model that explains the observable universe. According to this theory, the universe began as a hot, dense point nearly 13.8 billion years ago. This initial state, often referred to as a singularity, was infinitely small and incredibly hot. But then, in a fraction of a second, it started expanding rapidly in a hot explosion, and it has been expanding ever since. The term Big Bang was actually coined by British astronomer Fred Hoyle, and it's a bit misleading. The Big Bang wasn't an explosion in the traditional sense. Instead, it was an explosion of space itself. It's not that the universe began as a tiny point in space and then exploded outward. Rather, space itself began small and has been stretching ever since, carrying galaxies along with it. But how do we know this actually happened? There are several key pieces of evidence that support the Big Bang Theory. Firstly, we have the redshift of distant galaxies. When we look at distant galaxies, we find that their light is shifted towards the red end of the spectrum. This is known as redshift, and it's similar to the Doppler effect that changes the pitch of a siren as it moves towards or away from you. In the case of galaxies, the redshift suggests that they are moving away from us. And the further away the galaxy is, the faster it's moving away. This suggests that the universe is expanding and that it was once much smaller and denser. Secondly, we have the cosmic microwave background radiation CMBR. The CMBR is a faint glow of radiation that fills all of space. It's the afterglow of the Big Bang, the cooled remnant of the hot, dense state of the early universe. It was first detected accidentally by Arno Penzias and Robert Wilson in 1965. The Big Bang Theory tells us that the universe began as a singularity, a point of infinite density and temperature. But what does that mean? And what was there before? A singularity is where our understanding of physics, as we know it, breaks down. It's a point where space and time cease to exist. This concept comes from Einstein's theory of general relativity, which describes how mass and energy interact with space and time. But general relativity is a classical theory. It doesn't account for the strange world of quantum mechanics, which describes the behavior of particles on the smallest scales. When we try to apply quantum mechanics to a singularity, we get answers that don't make sense. So, what was there before the Big Bang? The truth is, we don't know. According to general relativity, time itself began at the Big Bang, so there may not have been a before. But this hasn't stopped scientists from speculating. Some suggest that our universe is just one of many in a multiverse. Others propose that the Big Bang was not the beginning, but just a phase in an eternal universe that expands and contracts cyclically. One popular idea is cosmic inflation. This theory suggests that the universe underwent a rapid expansion after the Big Bang, smoothing out irregularities and creating the large-scale structure we see today. According to some versions of this theory, inflation could be an ongoing process, giving rise to an infinite number of universes in a vast multiverse. Another idea is string theory, where the fundamental constituents of reality are not particles, but tiny, vibrating strings of energy. String theory could potentially provide a quantum description of gravity, solving the problem of the singularity. These ideas are fascinating, but they are highly speculative. We don't yet have any empirical evidence to support them, but they represent our best attempts to answer the profound question of what existed before the Big Bang, the formation of galaxies and stars. In the vast expanse of the universe, billions of galaxies spin, each a whirlpool of stars, gas, and dust. But how did these cosmic islands come to be? Let's journey back in time to the moments after the Big Bang. In the immediate aftermath of the Big Bang, the universe was a hot, dense sea of particles. As the universe expanded, it cooled, and these particles began to combine to form atoms, mostly hydrogen and helium. These atoms didn't stay alone for long. Under the influence of gravity, they began to clump together. Over hundreds of millions of years, these clumps grew larger and larger, forming the first stars and galaxies. But how did this process happen? How did matter coalesce to form galaxies, stars, and planets? The key is gravity. Even though the universe was almost perfectly uniform, there were tiny fluctuations in density. These fluctuations acted as seeds, pulling in more and more matter through gravity. As these clumps of matter grew, they became denser and hotter. Eventually, the pressure and temperature at the center of these clumps became so high that nuclear fusion ignited, creating the first stars. These stars didn't exist in isolation. They were part of larger structures, galaxies, vast islands of stars held together by gravity. But there's more to galaxies than just stars. There's also dark matter. Dark matter is a mysterious substance that we can't see directly, but we know it's there because of its gravitational effects. It's thought to make up about 85% of the matter in the universe, and it plays a crucial role in the formation and evolution of galaxies. But there's another mysterious player in the cosmic drama: dark energy. Dark energy is a form of energy that permeates all of space and is driving the accelerated expansion of the universe. So, from the primordial soup of particles, under the influence of gravity, dark matter, and dark energy, the universe as we know it came to be. Galaxies spun into existence, stars ignited, and planets formed. And on at least one of those planets, life evolved. That's us, the product of billions of years of cosmic evolution, the future of the universe. As we gaze into the night sky, we are not only looking into the depths of space, but also into the future. What will become of our universe billions, even trillions of years from now? Scientists have proposed several theories about the future of the universe, each painting a different picture of what's to come. Let's explore some of these cosmic destinies. The first scenario is known as the Big Freeze, also referred to as in heat death. In this scenario, the universe continues to expand and stars burn out, leaving behind white dwarfs, neutron stars, and black holes. Over time, these remnants also decay, leaving a cold, dark universe filled with diffuse matter and radiation. The second scenario is the Big Rip. This theory proposes that the expansion of the universe isn't just continuing. It's accelerating due to a mysterious force known as dark energy. If this acceleration continues to increase, it could eventually overcome gravity and tear apart everything in the universe, from galaxies and stars to atoms themselves. The third scenario is the Big Crunch. In this case, the expansion of the universe eventually slows down and reverses. Galaxies, stars, and ultimately all matter are pulled back towards a central point, leading to a universe that collapses in on itself. This could potentially lead to another Big Bang, in a cycle of cosmic birth, death, and rebirth. These are just a few of the theories about the future of our universe. Each one is based on our current understanding of physics and cosmology, and each one is a testament to the power of human curiosity and imagination. But the truth is, we don't know for certain what the future holds. The universe is under no obligation to conform to our theories or expectations. It will continue to evolve according to its own laws, in ways that we can only begin to imagine. And so, as we look up at the night sky, we are left with a sense of wonder and a touch of humility. We are part of a grand cosmic story that is still being written, a story that spans billions of years and countless galaxies. And no matter what the future holds, it's a story that we are privileged to be a part of. And so, as we journey back to the dawn of existence, we find ourselves in the presence of a singularity, a point of infinite density and unimaginable heat. From this singularity, the universe as we know it was born, unfurling in a spectacular event known as the Big Bang. This cosmic explosion didn't just give birth to matter and energy, but to time and space itself. In the blink of an eye, the universe expanded, cooled, and gave rise to the first atoms, the building blocks of everything that exists today. Stars ignited, galaxies formed, and the cosmic ballet began. But this is not just a tale of cosmic bodies. It's the story of us. For we are not just in the universe, we are of the universe. Its atoms form our bodies, its stellar furnaces forge the elements we need for life. The story of the universe is still being written as it continues to evolve and expand. And as curious beings, we continue to explore, pushing the boundaries of our knowledge, seeking answers to our origins and our place in this grand cosmic tale. The universe began as a singularity, but it gave rise to a magnificent reality. A reality in which we live, wonder, and seek to understand the mysteries of the cosmos. And perhaps that is the most extraordinary part of the story.